paradoxes which were popping up. And a man named David Hilbert, who really wanted to clear up all these ideas of paradoxes which arrived in mathematics, he really felt that, David Hilbert felt that mathematics was our most sure and certain source of knowledge, that if there was any flaws in mathematics, we were doomed as far as human beings in terms of knowing true things. And the paradoxes which I speak of really refer to two main things. One is this issue kind of Euclidean versus not Euclidean. This was a revolution which started happening in the 1800s, and people slowly started dealing with over those 100 years, entering 1900. But then there was, right towards the turn of the century, the two set theory paradoxes, and these were paradoxes which I talked about earlier. And that was the idea of the Barber Paradox. And for those of you who weren't here for the first lecture, the Barber Paradox says, suppose we have a town where a barber shaves all people and only those people who don't shave themselves. Well, then who does the barber shave himself, or does he not? And kind of by the definition, by the way we set up the town, it appears to be a contradiction, because if the barber does shave himself, then according to who the barber shaves, he doesn't shave himself. And if he does shave himself, then if he doesn't shave himself, then he should. So it's a contradiction. And this was really, we thought that this was a paradox deriving from set theory, and we felt that set theory was going to be our sure and certain foundation of knowledge. We thought we could deal with these paradoxes. David Hilbert was huge. He said, guys, look, there is no unknown. Mathematics has to have a sure and certain foundation, and we should be able to establish as kind of a model system consistency and completeness of number theory. And he felt that number theory, if anything which is true, it's got to be number theory. And I always like doing this poll, but I want to ask you guys to vote. And I want you to decide the truth of the following. The sky is blue, and 1 + 1 = 2. So imagine, of all the possible worlds, which do you feel like is more true? The fact that the sky is blue, or that 1 + 1 = 2?
The second one.
So you feel like the second one should be true. Do you feel like it's true in all possible worlds?
It has to be.
So you don't think there's any universe out there where 1 + 1 could not equal 2? Okay. What about anybody else? Does anyone feel like, no, come on, this isn't even perceptual. What is this statement about? It's about these abstract entities which I just kind of created and wrote down on a piece of paper. It has absolutely no perceptual foundation. The sky is blue. I look outside, and what do I see? But I see the sky is blue. So what is that? So surely what I see has to be more true than this. Is anyone willing to defend sky is blue over 1 + 1 = 2?
Your senses are fully here.
True. So René Descartes was huge on this. He was like, what if this is all a dream? You know, what if this is the Matrix, Neo? All right, like this is exactly what he said. But what if we were to base our arithmetic on something else? Suppose we based our arithmetic on raindrops. So suppose we have one raindrop and another one, and we define addition as when they meet. So one raindrop plus another raindrop just gives me another raindrop. So in this system, 1 + 1 = 1. And what's wrong? I mean, this is perceptually validated. When I'm driving down my car, 60 miles an hour, and I have rain hitting my windshield, and I see raindrops merging together.
Maybe you should measure the size of it or something.
Okay, exactly. So there's all sorts of problems with identity. There's problems maybe with how the system's formed, but even in mathematics, we have to be very clear with what we're stating, what kind of field we're working over here. Because suppose I'm actually working over the integers mod 2, modular arithmetic, and that just says if it's divisible by something, I say it's 0. So when I do modular arithmetic, when I do mod 2 arithmetic, 2 mod 2 is 0. So 1 + 1 over the integers mod 2, it's not 2, but it's actually 0. So I mean, there's all sorts of things we have to deal with, and it's some uncertainties. But still, like, these are all rigorously defined. I could say, well, I'm just working over the integers, so I know this is fine. 1 + 1 is equal to 2 in all possible worlds. So Hilbert felt like, really, this has to be it. Like, mathematics has to be it. Number theory has to be so sure and certain that there's got to be no problem. But what Kurt Gödel did is he established two things. And these are going to be his two incompleteness theorems. One we're not going to really talk about so much. And I'm not going to work through all the proofs of these, but we're going to try to get an idea of what each of them mean. The first one is that any system as powerful as number theory and I'm just going to let NT be number theory. Which can prove its own consistency that system is necessarily inconsistent. Exactly. Somehow the second a system as powerful as number theory is able to talk about itself, things go haywire. If it can actually prove that, here I am, number theory, saying, look, I promise you guys, you can actually prove from me that I'm internally consistent. Well, any system which can talk about itself in that way is necessarily inconsistent. And, you know, this is really kind of a nitty-gritty proof, and I can't even give you all the details. So the second one, and I'm just going to go ahead and start it over here, is any system as powerful as number theory, so I'm just going to kind of go ditto, is necessarily incomplete. So this means that any system which is as powerful as number theory automatically looks like this. There are true statements which we can formulate which are not provable. And I'm going to go ahead and give you guys an example, an English language example of a statement which is, yeah, go ahead, Rishi.
What does it mean to be as powerful?
Good question. And this is, I'm going to explain this a little bit, but the idea is that in order to prove Gödel's incompleteness theorems, he had to use a very interesting trick, and that's called Girdle numbering. But first I want to give you this sentence, and then I'll tell you where that comes into play. So here's a statement. So put that up here. I'm going to put you star. And if we forget what the star means, it's Rishi's question. So let's just try to remember that. So let's consider a question, or the following statement. I talked about the liar paradox, right? I said, what happens with this sentence? So this statement is false.
Escher said that you can't, in your language, you can't say things like that.
Okay, very good. And why wouldn't we be able to say things like this?
If you have like a logically perfect language, you can say, you shouldn't be able to say things like that. But then the problem will be like, how can you tell that you can't say something like that?
So what is the problem exactly with, if you were to design your perfectly logical language, what would you rule out? What would you prevent sentences from doing that would prevent something like...
Talking about themselves.
There you go, exactly, self-reference.